Okay, thank you everybody. Welcome to listen to my presentation. And we are a team, Duckling, and my name is Wen-Chieh Fang, and we have also another team member, Henry, and he will, and me, and I and him will present our project, our work. Yeah, the title of the slide is that a boosting approach to predicting ALSFRS slow for the PRO-A database, and we come from National Cheng Kung University in Taiwan. This is the outline of our presentation. We first introduce the challenge, and then we give the details of the methodology. Then we give the lessons, and finally we give the conclusion. The lessons and the conclusion will present by Henry. Okay. And in this challenge, we tackle with the ALS disease, and this is a very serious disease. And during the 2014 years, there is a famous challenge that is called Ice Bucket Challenge. It wants to tell people that the ALS disease is an important disease. And there are many well-known people join this challenge. So this ALS is paying much attention all over the world. Okay. Here we give the problem definition of the SubChallenge 1. We want to predict 3 to 12 months of ALSFRS slope using the clinical trial data collected through the PRO-A database. And this database contains 7,200 patients from the PRO-A database. And there are 3 million data instances, more than 100 features, including time from onset, age, and FVC, site of onset, and so on. And finally, we want to use 3 performance measures to measure our performance. One is the concordance index. That is the area under curve of the ROC curve. And the second is the Pearson correlation. And then finally is the Lund mean square deviation. Okay, then finally we'll combine these 3 scores into a single one to measure the performance. Okay. And here we first introduce what is the ALSFRS. It contains 10 symptomatic categories. For example, the speech. For example, the speech and the salivation, swallowing, and handwriting, and so on. All these 10 categories. Then we combine these 10 scores into together. Then we calculate the slope. The slope is the fraction of the ALS between 3 and 12 months. Okay. So this is the final score. So here we introduce our methodology. On the right side of this slide, give the flow chart of our method. And this is a traditional flow chart when we want to predict the slope. First, we collect the data, and we use the training data and the readable data as our total training data. Then we train our prediction model. So the input of the predictor is the six top features. Then finally, we use the 3 performance measures. So the validation data is used for the validation. Okay. So there are 3 important phases in our methodology. One is the data preprocessing, and one is the feature selection, and finally is the prediction approach. Okay. So in the data preprocessing, we first observe the missing values, and we find that in the data set there are many missing values. So we disregard those features with which 90% of the values are missing. Then for the remaining features with missing values, we impute the mean of that variables, okay? And in the ProA database, there are two kinds of feature types. One is the static feature. These features with only one value per patient. For example, the age, everybody has one age, okay? And the gender. Then the second type of feature is the time resolved, or we call time-dependent features. These features with different values when time varies, okay? And in this challenge, we test the minima, maxima, and the mean as the features for the time-resolved features, okay? And here is the most important part of our feature selection. And we can see on the right side of the slide, first we ran the features by their information gain. Later I will introduce what is the information gain. So we have a ranking of the features, and from the top features, we examine several combinations from the top ranking features, and we compare their performance using the cross validation to find the best feature set. Okay. Because we want to calculate the information gain, but remember that the slope is a continuous variable. So we first need to do the binning. So in this challenge, we apply the equal frequency binning that divide the response variable into several groups. In our method, we divide the output into 3 groups, such that each group contains almost the same number of values. Okay, so in this way, we can then calculate the information gain. Okay. In the information gain, we need to first calculate the entropy of the output. The entropy, we can see it is the uncertainty of the output, and then we calculate the conditional entropy. This is continuous entropy is given that we have a feature. Then what is the entropy? Is the entropy. Then finally, we use the entropy and the conditional entropy to calculate the information gain, or it is also called mutual information. It is the information we know of the output minus what we know of the output given the specific feature. So the information gain is the entropy Y minus given the feature of the entropy Y. So this is the information gain. Okay. This concept is based on the information theory. Okay. So from this feature selection, and we also use the cross validation to find the best feature set. This is our top 6 features, and in the Nita slide there is some error. So this is our final top 6 features. The first one is the onset delta. It is the time in days between the symptom onset and the trial onset. And the second feature is the trunk. For example, how you can dress in, your hygiene turning in bed. And the 3 is the phosphorus. It is related to the level of calcium. And it is associated with the kidney function, our body kidney function, and the nutritional status. And the 4 is the speech, our speech ability. And the 5 is the cutting, the ability we cutting the color food and handle the utensils. Okay. And the final is the leg, the ability to walk it and the climbing stairs. So this is the top 6 feature we finally select. Okay. Then in the prediction approach, we use the 7,200 patients data, and we also combine the leaderboard data as our total training data set. And then we choose the state-of-art prediction algorithm gradient boosting. Here I will introduce the gradient boosting, okay? The gradient boosting combines several weak estimators. Here is the regression tree or decision tree into a single model in a forward stage wise fashion, okay? Then at each stage, there is some imperfect model. This model F is not very good, but okay, it's fine. And we use the gradient boosting improves on it by adding the weak estimator HM, which it fits the residual. Residual is the output minus the FM. Okay. So finally, the gradient boosting produces a new model. M plus 1 equals the previous FM plus the HM. So each HM minus the model's mean square error. The mean square error is the loss function over the training set. And this process is repeat, and until the maximum allowed number of weak estimator is reached. So, and we may wonder like why it called gradient, because the residual y minus fn is the negative gradient of the loss function. So this is what we call gradient boosting. It is also a famous ensemble approach in prediction algorithms. Okay. Okay. Then the next slides will introduced by Henry. Okay.
Hi everyone, I'm Henry, and I will show you the process we do and the lesson we learned. When dealing with this question, we mainly use R and Python. We extract the features in R, and then we build our predictor in Python. And also we use the very good tool called Orange. It's an open source data visualization and data analysis software. Okay, and now I'm going to share the lesson we learned. First one is feature selection is a very complicated and very important things to do. And it can be done very simple. Like in Python or R, there's a lot package to do the feature selection, to rank the feature. There's some criteria like Gini ratio or mutual information that can select the data. However, also in our first, when on a leaderboard, we just use the information gain and select the top 6 features. And then, however, I see that there's a room to improve is that actually we should consider how features are correlated to each other, and because we input the data when there's some missing data, so there's some features that contain a lot of missing data, and then so it should also we should also consider it. So so our compound way to do the feature selection is that we rank the feature first to generate the feature like candidates for like maybe 20 or 10. And like we try a lot of combination, for like hundreds of combination, and then see the performance on the cross-validation. And then we choose the best feature set. So it's like you can look at this picture, and we rank the features based on information gain first, but we don't just select the top 6 feature, because, for example, like maybe some features are highly correlative. Since you adopt like Q1 speech, and then if you pull a very similar one, maybe it's not that helpful. And then so that in the final submission, we just try a lot of combinations through the like feature candidates. So we use the one with the best performance on cross-validation. And then also I want to share that the importance of validation framework. Since after the validation framework is done, and you can try a lot of new ideas and then see how good they are based on the performance on the cross-validation score. And also, we can see after the data, after the leaderboard data were released, we can also test our data on the test our model on it and see how is the performance and see how it deviates from our expected outcome. And in the final summation, we used training data and leaderboard data. We combine them together to generate our model. And then another thing I want to share is keep thinking ways to improve model. And it's like there's after the first attempt is done, and we can visualize the whole process and like brainstorm new ideas. Like we wrote down the all steps we took and all decisions we made, and like this we done the pre-processing, feature selection, training, prediction, evaluation. There's in each step there's some rooms to improve. For example, like the in pre-processing we impute with the missing data with min, but we can also try for median value or KNN algorithm. And for feature selection, it's also good to try like different ranking criteria. And for the prediction, because of the time limitation, we didn't try the ensemble different models to predict. We just used gradient boosting. So I think maybe, yeah, if we like ensemble different methods, maybe random forest or another models, and we ensemble it together, it will get a like better performance. Okay, and then in conclusion, I think the feature selection is a very important thing that we have to like take. We can put more emphasis on it, and the good performance I think is come from the like careful data preprocessing and like best feature set and the state-of-art predictor. And we also found that tree-based ensemble methods are usually perform better than GLM in SubChallenge 1 and 3, which is predicting the progression slope. We tried GLM, we tried different regression method, but it doesn't perform so well. And however, on the question 2 and 4, the data is right censored. So usually we also tried Cox model, but we haven't found a like tree-based method to outperform the Cox model. Yeah. And thank you for your attention. It's our team. Thank you.
Thank you very much. So I think we have time for one or two quick questions. Yeah, so actually, I have one. So you decided to use a combination of information gain and sampling for selecting features. So what was the reasoning not to do a full wrapper approach? A wrapper approach that just uses kind of your predictor in order to do combinations of features and then decide on picking the best subset.
What kind of method to pick?
Yeah, so wrapper is like when you take your prediction method and then do predictions just on subsets of features without using a different metrics like information gain to pick the best features.
The forward or backward selection? I mean, the subset of the features?
Yes.
like the top 6 and use the subset in the top 6.
So I'm asking, why did you use the information gain?
The information gain, I think it calculates the correlation between the feature and the label. So like it's like to calculate the individual importance, like in the thing that we have to predict. So I think we rank the features based on the information gain, so that we don't have to like if we use all features and find a subset 6 feature inside. Maybe at first the raw data have like hundreds of features, so there will be the time complexity is like you have to consume too much time to So if we use feature information gain to rank the feature, maybe we can select the candidate first, maybe 20 candidates, so that the selection will be easier because we shrink the size of the features. Okay. Thank you.